So what are the key things you need to know about momentum? In this video, I'll try to tell you. So here we go. First of all, momentum symbol is P. It's a vector. It's given by m times v. V is a vector. So that means it has direction. So momentum is just mass times velocity, like that. Now the neat thing about momentum is that it's conserved. You can have all kinds of different collisions where things bend or they don't bend or they bounce off. We'll talk about that later. But in those cases, there's a difference between whether energy is conserved or not. When things are crumpled, energy isn't conserved. But no matter what, momentum is always conserved. So that's kind of useful. So that means that the initial momentum, whatever it is going to equal the final momentum when you add everything up. Okay? So we got that. Now let me give you a quick example of a one-dimensional collision in which we have conservation of momentum. Okay? So here's an example that I used in class. Imagine you got two hockey pucks. One of them has a velocity of 0, and one of them has an initial velocity. And so this one's traveling like that. Now we put Velcro in these guys so that when they collide, they're going to stick. And so after they collide, it's going to look like this. So they're stuck together, and they're traveling off here with what we'll call a final velocity. We want to know what that final velocity is. Oh, and by the way, each of these guys has a mass of m. And now when they're stuck together, you have 2m. So the total momentum in this situation here is only accounted for by the puck that is moving. So that's the mass times the initial velocity. Now that must equal the final momentum in this situation over here, which is the mass, and now it's 2m because they're two pucks stuck together, times v final. We want to solve for v final in terms of whatever v initial was. So I set these guys equal to each other because the initial momentum equals the final. I can cancel out m's, and I get the initial velocity, whatever it was, divided by 2 is going to equal the final velocity. So when these two guys collide, what happens is basically it ends up going half the speed that the original puck, the solo puck on the left, was traveling. So that's a useful type of example of a one-dimensional collision. We can also have in two-dimensional momentum is also conserved. So let's just go over a quick example of that. So I think I gave something like this in class. Imagine we've got a grid, streets like that, and then we've got a diagonal street like this. And we've got some kind of ambulance that's traveling this way. It's got a little siren on top. That's how you draw that with that little thing there. And then on this street here, we have a sports car, and the sports car is traveling like this. And each has got its own velocity like this. I'm just going to graphically explain what happens. Now these two cars, they smash into each other and they create some twisted wreck. And the twisted wreck skids off kind of like this. And so you have something that looks, like that, and there's the little thing. All right, and this comes in at an angle, let's say theta, and it goes out together at an angle alpha. You go, well, how do you solve a problem like this? And what we know is that the initial momentum must equal the final momentum. So the initial momentum of the two cars coming together, and that's given by this system here. That's the initial momentum. And then that's going to be basically equal to the final momentum, which is this traveling there, and that's this. So these guys have to be equal to each other because there's conservation of momentum, even if you have a smashed up car. So now what I'm going to do is draw different components to these guys. And you have to draw the x and y components. The basic idea is this. The initial momentum in x is going to equal the final momentum in x. The initial momentum in y is going to equal the final momentum in y. So let's draw these different components, and let me try to use some different colors here. So I'm going to draw the y component of this car. Its momentum is like this. So it's the mass of the car times its velocity. All right. Now I'm going to draw the y component of this car. It's going like that, and that's going to be the mass of this car, and I'll call it m1, and let's say that's v1, and this is m2 and v2, okay? So these y components are like this, so I get something that looks like this initially, and something that looks like this initially, and finally, I'm going to have some y component that looks like that. And somehow when I add these two together, they have to equal this. okay? And this is twice the mass. So this is mass 1 plus mass 2 times some final velocity in the y direction. And this is going to be mass 1 times velocity 1 in the y direction. And this is going to be mass 2 times velocity 2 in the x direction. So this is all the y momentum right here, just graphically representing it, okay? Let me pick a different color for, let's say, in the x direction. In the x direction, we have some momentum going this way. So that's the momentum in the x direction. And that's going to depend on mass 1 and velocity 1 in the x direction. And now notice in this other car, we have absolutely no x component at all. It's only in the y component. So there's nothing else going on. Nothing else going on. So what we want to do is now somehow see if this particular momentum is going to be equal to this momentum here. And this is mass 1 plus mass 2 times some velocity final in the x direction. And so that's going to look roughly like this. So that's mass 1 plus mass 2 times velocity final in the x, like that. And so this portion here is all telling us how we add things up. So what you have to do in this problem is you have to add in the values. You got to put in the mass of that one, the velocity of this one in the y direction, the mass of that one, the velocity of this one in the x direction, the joint mass, and then the velocity in the y direction. Now you might go, well, I don't know. How do I get the velocity in the x or the velocity in the y? Real quick, here's how you do it, just to remind you. Let me go back to black. So if I have a triangle like this car coming in, so I got something like that, and I said it was coming in at angle theta. And so this, remember, is the ambulance. So the ambulance looks like this. And it's got a mass of 1, and it's got a velocity of 1. So that's its just mass and velocity. It's traveling like that. Now, in order to get the different components, what I'm going to have to do is say this is mass 1 times the velocity in the y direction of 1, and this is mass 1 times the velocity in the x direction of 1. Okay, so it's going like this, and this one's going like that. How do I get these components? I treat this as the hypotenuse. I treat this as the opposite side. I treat this as the adjacent side. And I know my angle. So I can say something like this. Sine of theta equals opposite over hypotenuse. And so that's going to equal the opposite side, which is the mass of 1, okay, like that, times v1, like that, in the y direction. The hypotenuse is the mass of 1 times the overall velocity, something like that. So I can multiply and say the mass of the ambulance times its velocity times sine theta is going to equal the mass of this ambulance times the velocity in the y direction. This guy cancels with that guy, and you basically get v sine theta is equal to the velocity in the y direction of velocity 1. So you're going to have to do that with the other one, and if you do that with this one, you're going to get v1 cosine theta is the velocity of 1 in the x direction. So this is how you do it. And you've got to get these different components that I just talked about, the velocity of 1 in the y direction, the velocity of 2 in the x direction, the final velocity in the y, the final velocity in the x. These are the things you have to pay attention to using trigonometry like that, given the angle. So this is a quick review of momentum. Momentum is defined by m times v. It's always conserved no matter what kind of collision you have. In a 1D collision, I've worked out an example here for you. And here in a 2D collision, I've kind of given you the basics of how it works. So I hope this has been helpful. Please feel free to leave comments or give me suggestions for what to do next. Thank you.